So let's get started with thinking about the dot product. The dot product is going to be a way of taking two vectors and producing out of those two vectors a single number. So sometimes the dot product is called the scalar product in other contexts because the answer to a dot product, the result, the output of a dot product, is a single number. So it takes two vectors and it spits out a single number as its output. And so the preview activity in this section actually defines, in 2 dimensions at least, what the dot product, or how we compute a dot product. If you give me a vector with components u1 and u2 and another vector with components v1 and v2, to find the dot product, we're just multiplying the first components together, so u1 times v1, and we're multiplying the second components together, u2 times v2, and then we are adding the results. Right? So it becomes a sum of products of components is a way we can think about the formula for computing a dot product. And so the purpose of the preview activity, and it's got a number of parts, and I want to kind of chunk them up a little bit and just have you discuss them one at a time and write them up in your team worksheet as you're going along. The purpose is to first get us used to the computational aspects of what a dot product is, and then start to introduce some of the geometric interpretation. So in part C, you'll figure out how the dot product relates to the magnitude of a vector. And then in parts D and E, it's sort of an introduction to how the dot product tells us something about the angle between vectors. So all the parts of this activity are very important for setting the stage for the work that we're going to do. So to get us started, what I'd like to do is give you all, as a group of 4 today, an opportunity to, first of all, just go through parts A and B, which are the computational elements of the dot product, just to get us used to using it. So let's take no more than 5 minutes. This will probably take more like 2 or 3 to have a discussion of those 2 parts, part A and part B. I'm going to put a 5-minute timer up here, but we'll probably reconvene after 2 or 3 or whenever you're done discussing just parts A and B. So I've divided up the activity today so that there's a space right after part A and B for you to put your responses to that part. So let's use that as a way to get us started. I'll put a 5-minute timer up, and then we'll probably reconvene as soon as as soon as I feel like we've got what we need to out of these first couple of parts. So far so good. You computed the dot product of these vectors u and v, 3 times -2 plus 4 times 1, which, again, when you do that dot product, the result of that dot product needs to be a single number, right? So you get -6 and you get 4, but you have to add them together to get -2. That's the dot product of those 2 vectors. And then in the second part, you're asked to do that dot product with the vectors I and itself. And here I is the unit vector in the x direction. So I means 1, 0. And j is the unit vector in the y direction, so it means 0, 1. So you found that those dot products were respectively 1 when I take the dot product of I with itself, and 0 when I take the dot product of I with j. Then in part C, when you took the dot product of u, 3, 4, with itself, you got 3 times 3 plus 4 times 4. It ends up being 25. And you speculated that when you take the dot product of a vector with itself, it's related to the magnitude in that it is the square of the magnitude. So each of your groups said it in a slightly different way. This group said that the dot product of u with itself is the square of the magnitude of u. And the other group just had the shoe on the other foot, that the magnitude of u is the square root of the dot product of u with itself. So those both mean the same thing. So what we're seeing already here is that the dot product is giving us some information about length. Right? That the dot product by itself can kind of reify this notion of magnitude, norm, length of a vector that we looked at yesterday. So that's one nice thing about the dot product, is it carries information about length, about magnitude. And so what we want to do next as the activity moves forward is figure out how the dot product also carries some information about angle in it as well. And so for these next couple parts, I actually have, just to help with the computation and to keep the focus on the concepts here, I have a Desmos worksheet that you are welcome to use as part of the next part of this activity. I'm going to put that link into the chat here. Because the goal of these next parts are to figure out how the dot product carries information about angle. And so in part D, you're asked to plot the vector 1, 3 and the vector minus 3, 1 and find the dot product. What is the angle between those vectors? And then to repeat using 1, 3 as one of the vectors and then using a selection of 5 other possibilities for the second vector. So this is why I like using a calculator to do this part, just so that we're not spending all of our time on arithmetic. And so the main question here that you're addressing is, what does the dot product of two vectors tell us about the angle in between those vectors? So feel free to use this Desmos worksheet to streamline your calculations and do parts D and E of this preview activity. All right, so you figured out that when we have vectors that make an acute angle with one another, so let me go to a zoom square here. When vectors make an acute angle with one another, we end up with positive dot products. When vectors make obtuse angles with one another, we end up with negative dot products. And the in-between case, right, when two vectors make a right angle with one another, when they're perpendicular, sometimes we use the fancier word orthogonal for that, the dot product is 0. So that's a sense in which the dot product carries some information about angles, right? Acute angles, positive dot products. Obtuse angles, negative dot products. And right angle, probably the most important one, 0 as the dot product. And so we can sort of experiment further to kind of figure out what's actually going on here, right? That as I change, first of all, as I change the lengths of my vectors, this goes to the question that you had before, Peter, that as I change the lengths of my vectors, notice that the value of my dot product is actually also changing, right? So that, I think, is something we can expect because the dot product knows how to tell us the length of a vector, right? Because the dot product of a vector with itself is the square of the magnitude. But if I'm changing the, let's see, how do we do this? If I'm changing the length without changing the angle, I guess, right, then the dot product is getting bigger or smaller accordingly. But if I change the angle without changing the length, then, you know, we're also, again, changing the dot product. So what, I guess, let me sort of ask the question this way. If we sort of make a plot like the one that we have on the screen here, where the angle between my vectors is kind of the horizontal axis, and the dot product is the vertical axis, what sort of trigonometric function of our angle has the property that it is 0 when the angle is 90 degrees, and it is maximized, it is at its largest when the angle is 0 degrees, and is at its largest negative value when the angle is 180 degrees. What trigonometric function is doing that? What's being graphed here?
Cosine?
That's a cosine function. Yeah. Cosine function has the maximal value, maximal positive value at a 0 degree angle, has a 0 value at a 90 degree angle, and has its largest negative value at a 180 degree angle. Right? So that's what this gray graph over here is. It's the graph of the cosine function. And notice, what is the amplitude of this particular cosine function? What is the value of its highest point? What is the largest value that the dot product of the vectors v and w can take?
I think 1.
Sorry, say again?
I think 1.
Well, the largest value that the cosine function can take is 1. But this appears to be able to take a larger value, right? That the amplitude of this cosine function, the highest point, is the product of the magnitude of v with the magnitude of w. So the largest value that a dot product can take is the product of the magnitudes of v and w. So when v and w are parallel to one another, they make a 0 degree angle. The dot product really is just the same thing as multiplying the length of v times the length of w. Right? The dot product and the product of the magnitudes agree when my vectors are parallel. If my vectors are anti-parallel, if they make a 180 degree angle, then the dot product is the product of the lengths, but with a minus sign included as well. Right? And if it's anything in between, the cosine of the angle is the factor that we multiply by to find the dot product. So all of this is to say that the geometric idea of what a dot product is and how we can compute a dot product is that the dot product of two vectors is the product of their magnitudes multiplied by the cosine of the angle in between them. So this is the more specific way that a dot product carries information about both lengths and angles at the same time. And so what's cool about the dot product is that we can use the dot product to determine the angle between two vectors, to actually compute the cosine, and then we could take the arc cosine of that to actually get the angle itself in radians or degrees, whatever mode you happen to have your calculator in. So that's where we want to go next, is to do a couple of problems just to get used to the idea of using dot products to compute angles. So now that you've had a little bit of practice using the dot product to find angles, right, by taking the dot product, dividing by the product of the magnitudes, and thereby getting the cosine of the angle. You can take the arc cosine of that to actually get a measure for the angle. That the sign of the cosine, whether the cosine is positive, negative, or zero, is probably a better way to say that, lines up with our understanding of when the dot product is positive, negative, or zero, right? Cosine is positive for acute angles, negative for obtuse angles, and is zero for right angles. So it lines up with what we expected based on the preview activity. Also, the next activity that we're not doing together is sort of physics flavored. We can use dot products to compute the amount of work done by a force as it acts on a body that's moving along a vector direction. And because the work is maximized, so the amount of work that we exert on an object is maximized when we're doing that work in the same direction as the motion, and is sort of the amount of work that it does on us is maximized when we're pushing in the opposite direction to the direction that it's moving, and that we actually do no work on the object if we're pushing in a direction that's perpendicular to the direction that it's moving in. That's what makes a dot product between force and displacement the right way to compute an amount of work done in physics. So this activity is just a little piece of that. So the next gear that we want to shift into here is into sort of putting a more precise point on the question, how much of one vector points in the direction of another vector? And so for that, what we end up talking about is a concept called projection. So projection is the last sort of topic that we're going to talk about in the dot product arena, and how projection works, so how we define projection for vectors, is as follows. Here we are. So if you give me two vectors u and v, I define the projection onto v of u, so the notation we use here is proj v of u, the projection onto the v direction of the vector u, is kind of an answer to the question, how much of the vector u points in the v direction, right? So it's a vector answer to that question. The way we would find it is by projecting, so perpendicularly projecting, orthogonally projecting the vector u down onto the vector v. It's almost like we're shining a flashlight above u and looking at the shadow that u makes down on the v direction. And so that's kind of where this idea begins, right? That the vector projection is sort of the shadow of u shining down onto the line which is determined by v. And what it helps us to do, actually, is it helps us to what sometimes we call resolve the vector u into a component which is parallel to v, that's the vector projection onto v of u, added to the orthogonal component. This is the component that we projected away. This is the perpendicular component, the projection onto the orthogonal complement of v, of the vector u. So we basically are writing u as the sum of a vector parallel to v added to a vector perpendicular to v, right? And this is useful in a lot of different applied contexts. For example, again, if we're thinking about physics examples, if u is the direction that I'm exerting a force, but v is the direction that an object is actually moving, then the projection onto v of u kind of measures the component of the force in the direction of the motion, and the perpendicular part of it is the component of the force that's perpendicular to the direction of motion. And when it comes to energy transfer and work and things like that, the parallel component is the only one that matters in physics. This perpendicular component doesn't contribute at all. So it gives us kind of a way of taking apart one vector into a part that's perpendicular to another and a part that's parallel to that other. So that's the idea behind projection. We also define one more idea, and that idea is called the scalar component of u along the v direction. And that scalar component is just the length of this projection. So the notation ends up looking kind of, a little bit daunting sometimes. But so the question is, how would we compute such a thing? And the short answer to that question is we can just use right triangle trigonometry to figure out, first of all, how to find the length of this side of the triangle, which we can do just by using a cosine, because cosine is adjacent over hypotenuse. The adjacent is what we're interested in, so it's the length of the hypotenuse multiplied by the cosine of this angle. But we know now how to find the cosine of that angle. It's the dot product of u with v divided by the product of the magnitudes of u and v. But then if I multiply by one more magnitude of u to find the adjacent side of this triangle, we get the scalar component right over here. A scalar component is the dot product of u with v divided by the length of v itself. And then if I want to find a vector that points in the direction of v, which has the length which is equal to this, then what I want to do is multiply this length by a unit vector in the v direction. And so when I multiply that by a unit vector in the v direction, a unit vector in the v direction is v divided by the magnitude of v. I get the vector projection, which is the vector v multiplied by this factor out in the front. And this factor out in the front re-stretches the vector v so that its new length is equal to this scalar component. So for my purposes, for the most part, when we do vector projections, this vector projection formula is the one that we end up using the most. So again, just to sort of underline what is the idea behind vector projection. Actually, I have a Desmos worksheet for this. So again, the idea is that the projection onto u, I think I have the notation backwards here. Let me fix that in real time, sorry. This is u and this is v. So the projection onto the v direction of the vector u is just something which is parallel or possibly anti-parallel to v, depending on whether u and v make an acute angle or an obtuse angle. And it's defined by this orthogonality, right? That if we draw the line from u to the projection onto v of u, that line is going to be perpendicular to the line determined by v. So we're just getting a right triangle here. The projection onto v of u could be longer than v, it could be shorter than v. It could be in the opposite direction as v. What do you think would happen if u and v are perpendicular to one another? What would the vector projection of u onto v be if u and v make a right angle? I just bend this to 90 degrees.
Essentially zero.
Essentially zero. We get not zero scalar, but the zero vector, right? The zero vector would be the projection of u onto v in the case where u is perpendicular to v. Because again, the projection is answering the question, how much of u is parallel to v, right? In this case, a lot of it is parallel to v because u is mostly in the same direction as v. In this example, it's kind of the opposite because u is more parallel to the opposite of v than it is to v itself. And in the case where they're perpendicular, there is no part of u which is parallel to v. It's entirely orthogonal to one another. So, last step in this section is just to get a little bit of practice with computing scalar components and vector projections using these formulas. So you can go back into the book again if you want to refer to the formulas for dot products and projections. But let's take about 5 minutes or so to do 9.3.5a. I'm leaving part C as something that you might want to do with your team after class. So what does the projection of u onto v actually look like? We sort of take v and we extend it out into an entire line. I guess let me try to align myself with the screen here. So we take v, we extend it into an entire line, and then we say how much of u lies in the direction of that line. And so we're kind of shining a light down onto this line and looking at the shadow of u down on that line. And that's what this vector minus 2, 4 is. So now that we know that minus 2, 4 is the projection, how could we find a vector that points from there to u? So that would be something perpendicular to this. Right? So how do we get a vector that points from one point to another point? We're going to be doing a lot of that actually today. So when we again, what's sometimes called resolve a vector into components parallel to and perpendicular to another vector. This is what we use the projection process for. So the part of U which is parallel to V, in this case anti-parallel, right, was this vector negative 2 comma 4, right? And then just by subtracting U minus this projection, or vice versa, depending on which way we want this vector to point. I think if we want it to point from here to U, then we want to do U minus the projection. And that's going to give me a vector that is perpendicular to V, such that if I add the parallel part plus the perpendicular part, I'm going to get U itself again. Right? So that's kind of the value of doing projections, is that we are able to sort of use, it's almost like creating a new kind of coordinate system. Right? Instead of having the x-axis and the y-axis as your parallel and perpendicular components, now we're using some other skew line as being kind of our x-axis, and the perpendicular to that as being like our new y-axis. So we can use projection to accomplish a change of coordinates. It's not something we're going to do very much. We probably aren't going to do it in this class at all. But it actually is the underlying philosophy behind a lot of different kinds of analysis in mathematics, including things like Fourier analysis, when we're analyzing signals to figure out what frequencies are in a signal in electrical engineering or something like that. What we're really doing is finding the components of that signal along each of the axes, which are determined by my pure frequencies. And then if I add up all of those frequencies with those prescribed amplitudes, I get my original signal back. It's all the same. I remember when I taught our applied math course a few years ago, I tried to start our semester with this idea, hoping that it would generalize up to that sort of infinite dimensional analysis that we do in applied math. It didn't quite come off the way that I hoped that it would, but it's the same philosophy. How much of this thing is in the same direction as that other thing? And that's what projection helps us to answer. So that will wrap up our dot product conversation for today.